Good day. We will make a video today about circle theorems as my students are asking for such. Let's recall that it falls under the topic of trigonometry and geometry. This channel itself is dedicated towards helping students who are struggling with CSEC mathematics, and we can see the link for it in the description down below. We also have a channel for students who are having problems with additional mathematics, and of course one for students who are having problems at the primary level or the SEA paper. So now that we're going to look at specifically circle theorems and where does that fall, this being the 8th topic on the syllabus for CSEC math, trigonometry and geometry, it can itself be subdivided into trigonometry or geometry. So today we'll be looking at geometry, which we know comes from the word geo, dealing with earth, and metry or metric, dealing with measure. So this speaks about the different measurements of circles or the earth. And we'll be looking at the specific topic of circle geometry today. And let's recall that circle geometry itself, when you look at what is being assessed, looks similar to this, where we have different shapes, triangles and quadrilaterals within circles, and how the angles are related. So let's remind ourselves of what happens when we're speaking about circles. A circle is a set of all points in the plane that are a fixed distance from a focus, a focal point, or a fixed point, which is known as the center. This, students, you will take this knowledge and expand a little further as you go upwards into your level of mathematics as you move to shapes such as ellipticals. So right now, just for us to remember circles, it tells us about the fact that one of the things is that the distance from any point on the circle to the center is called a radius. And a straight line joining 2 points on the circumference, on the edge of the circle, that is called a chord. And if we take this chord and we move it where it remains a straight line and it's going upwards, it's going to get longer and longer until it reaches its maximum length. And at that maximum length, the longest chord that is possible, because if it continues to go upwards, it will start to close down or the distance will reduce. So what can we say? The largest chord passes through the center of the circle, and that is called the diameter. As we review the basics of circles, let's recall arcs and sectors. And if we have a circle here with a piece cut out, an arc is a part of the circumference or the edge of a circle. And we will have a minor arc, as we see brought up in purple here. And a minor arc will be any arc which is less than half the circle, less than 180 degrees. And if we have a minor arc, then of course we can have a major arc, which is in black. And this angle will be more than 180 degrees. And in the area between the minor arc and the two radii, remember radii is plural for radius, that is called the smaller or the minor sector. And if we have the area between the major arc, which we have in black, and the two radii, that is the major sector. And as we move on with the basics, just as we refresher, segments of circles. So if we consider a circle here, and we have a line that cuts or touches the circle at only one distinct point, that is called a tangent. And you can imagine a ball resting on the table that point where the ball and the table touches, which is only at one point, the table is at a tangent to the ball. Or if it's leaning up against a wall, the wall and the circle will be at a tangent. A line that cuts a circle at two distinct points is called a secant. From A to B is the chord, and if it's a longer line, it's called a secant. This, however, is not to be confused with what we do in trigonometry. In trigonometry, cosine theta, we are well aware of that. And 1 over cosine theta is called secant theta or sec theta. So secant is not to be confused with 1 over cos theta. The area between the chord and the major arc, as we highlighted here, is the major segment, while the remaining part between the minor, while the area between the chord and the minor arc is the minor segment. So let's go on with congruent, similar, and symmetry of circles. So any two circles with the same radii are exactly alike. They have the same radius, the same diameter. If we rotate it, they're still going to look the same. So they're considered to be congruent. But if we have one circle and any other circle with a different radii, then they're considered to be similar circles. We have come across these terms of congruent and similar in triangles as well. And of course, all circles have infinite lines of symmetry. Imaginary lines where we can fold the circle along that line and it folds directly onto the other part or into two equal parts or halves. So let's actually get into the circle theorems. So the first one, we have a little circle there in green and we have the center highlighted. So the angle subtended by a chord AB. So what does that mean? It means if we have a chord AB where A and B are points on the circumference, not necessarily that we're drawing a line AB across, but we're using any 2 points on the circumference. If we had connected them, that would be a chord. And if we now connect that to the center, meaning we're drawing a line from A to the center and B to the center of the circle, the angle subtended, meaning the angle made by the chord AB at the center. So from A to the center, and that line turns until it reaches B to the center because those are two radii. That angle formed there, and you can try this. Any circle you want, pick any 2 points at random and connect it to the center. And when you measure that angle and we connect it to any point on the circumference now, we will see that whatever angle we get at the circumference will be half of whatever we get in the middle. Or let's say it again differently. The angle formed between A, the center of the circle, and B, for any circle you draw, is twice or 2 times the angle formed between A, any point on the circumference, and B. Now we're going to take the same rule and expand it because the rule is still the same, it just looks slightly differently. So let's look at the two radii that's starting from the center of the circle and going to A and one going to B. And if we open out the angles more and more until it becomes a flat line, this straight line now, let's redraw it. So we'll bring it across and form another circle. So what we had was two radii, A to the center and B to the center. And because it's flat, those two radii now becomes one straight line, or we can call it the diameter. And let's do the same thing. Let's connect from A and B to the circumference. So anywhere you want to do this, please try it yourselves with different size circles, different angles, and we recognize that the same rule applies. If we look at it, we can tell that AB, that is a straight line going across through the center. So that angle, which we had as 2x, is a straight line, or it is supplementary, meaning 180 degrees. And if we measure the angle at the circumference up on top, it will be half of that. So half of 180 degrees is 90 degrees. So this means that if we're having the diameter of a circle as one line or one side in the triangle, then the opposite angle will be 90 degrees. So this gives us a right angle triangle. Now, sometimes this is said slightly differently, but it's the same working and the same concept as the first diagram. So in the first diagram, if we look at it, that was a quadrilateral, 4 sides. The angle x was an angle within the quadrilateral, and the 2x was outside of it. We open the legs until it becomes a straight line or a diameter. The 2x is still measured on the outside, and the x is on the inside. So if we extract this, we will see that this looks like a half a circle. So for any semicircle, the angle in it is 90 degrees. So anytime we have a semicircle and we're drawing a triangle, then A to B, that diameter, is actually the hypotenuse, and it will always give you a right angle triangle. Now let's continue with what we are doing. Look at the first circle and the second. It's the same format, even though it looks completely different. It's the same rule. The angle subtended by a chord AB at the center is twice the angle subtended at the circumference. Let's show you another form. And here we're going to take the same 2 radii. Let's carry it across, bring up the circle, and let's carry it up even further. So now it's the same rule again. Look where A and B ended up. And if we draw the 2 lines so that it will make an angle at the circumference, then hopefully we can see it's the same one rule for all 3 completely different looking shapes, because they all fall under the same concept. As such, where will the angles be? The angle at the circumference will be on the inside, and the one at the center will be on the outside. And it will still follow the rule that the angle at the center is twice the angle at the circumference. So this may look as 4 different rules, but they're actually all the same. Let's go on to the next theorem. Let's bring up a circle, and we look at the angle subtended or made by a chord AB again, and we're going to look at it straight to any part of the circumference. So I want you to draw this shape and draw 2 lines from A and B connecting, meeting at any point on the circumference, and measure it. Whatever your triangle is, it may be 20 degrees, 50 degrees, 80 degrees, it doesn't matter. And now from the same points of the chord A and B, we're going to draw again another point on the circumference. So we got another triangle. And let's look at it. If we slide it down to the left, we have another triangle. And if you measure it, the angle is still going to be the same. So the angle subtended or made by a chord AB is the same anywhere in that segment. In this case, it's a major segment that we're talking about. So we could see from AB straight up in the red or maroon triangle, the angle formed at the top was X. And if we moved it to the left side, still because it started from A and B, it will still measure the same amount. So you check it yourselves and see it. And what about if we started it over and instead of moving to the left, we move to the right? We're still going to get the same size angle. So let's go on to another theorem now. When the tangent to a circle is joined, remember we spoke about a tangent being a line which is only touching the circle at one distinct point. And if we connect that straight up to the center of the circle, then we will form a right angle in 90 degrees. And of course, that line that's connecting the point on the circumference to the center is the radius. And if we consider now a chord, and we're trying to connect the chord to the center of the circle, and we draw a line straight across, please do this yourself. Any random line, you will see that it forms a 90 degrees and it bisects the chord. Let's go on now. So for any triangles where the triangle fits directly inside of the circle, meaning that all three corners touch the circumference of the circle, it doesn't matter where it is. So go, students, and draw any size circle, pick any 3 points and connect them. So we have a triangle which fits inside a circle. So it's called a circumscribed triangle because it's touching the circumference. And now let's consider the sum of all the angles inside the triangle will add up to 180 degrees, and we're going to prove that here as well. So let's recall the exact statement. The sum of the interior angles of a triangle are supplementary, meaning they add up to 180. And let's take a little proof of that. Let's look at the angle X, and it's highlighted by those two blue lines. And if we slide that across and turn it, it's the same angle X. Look, it's there now. And let's do the same for Y. We have it with two black lines. And if we translate it and then do some rotation, so we're transforming it across, look, we should recognize that X plus Y plus Z gives us 180 degrees. So it's a straight line. So when the two angles were translated and then rotated, they formed a tangent to the circle. And this happens every single time. So knowing that now, we can also state something else. Look where X is. X is on the outside of the triangle connected to the tangent. And X is also opposite the Z on the other side. So there's a theorem which states that the exterior angle between a tangent to a circle and a triangle, let's use the idea of X, is equal to the opposite interior angle of the triangle. So hopefully we can see X on the inside, opposite, and it's also on the outside of the triangle, between the triangle and the tangent. Let's look at Y. Does Y fit that rule? Y is the exterior angle between the tangent to the circle and the triangle, and Y is also the opposite interior angle of the triangle. So it works either way. These rules are best learned if you practice it 1 or 2 times with different circles and different tangents, and do the same thing here, and you'll see that they all line up. And the theorem holds for any triangle where the triangle is touching the circle at 3 points. And now let's look at a similar rule, but no longer for triangles. We're going to be looking at it for 4-sided figures. 4 means quad, and sides is lateral. So for any quadrilateral that are circumscribed, meaning that all 4 corners touch some part of the circumference, and let's name them A, B, C, D. So normally when we're naming shapes, if we're naming the corners, we use capital letters. And if we're naming the angles, we use common or lowercase letters. This is the standard way of doing it. And what we do when we're naming it, we try to go in one direction. So if we started with A up on top, then either BCD goes all in a clockwise direction or in an anti-clockwise direction. It's up to you. So now that we have A, B, C, D, let's see if we could get a relationship to connect them. So, of course, since if 4 sides of the quadrilateral fit within the circle, it's a special quadrilateral. It's called a cyclic quadrilateral. Not all quadrilaterals can be cyclic, but let's use for this particular case. So for cyclic quadrilaterals, look at this particular situation. Let's highlight C, that angle. We have it with 2 lines to show the angle, 2 black lines. And let's do the same thing again. Let's translate it across to A and rotate it. And what we will recognize is A and C gives us a straight line. So A plus C is equal to 180 degrees. Let's now do the same thing for B. We have 2 purple lines showing the amount of turn at B. And if we slide it across or translate it and then turn it, or the other word is rotate, we will see the same angle B came across. So B plus D will also give us a straight line of 180 degrees. So the opposite angles A and C or B and D add up to 180 degrees. So we can say the opposite angles in any cyclic quadrilateral are supplementary, meaning they add up to give us a straight line. S for supplementary, S for straight line. And of course, the exterior angle, just as we spoke about it with the triangle and tangent, the exterior angle of a cyclic quadrilateral, which is, let's say, up on top was C, is equal to the interior, meaning inside the quadrilateral, opposite angle. So look where C is, it's on the outside, it's the exterior angle, and C is also on the opposite interior angle. Or let's use B. B is on the outside at the bottom left in purple lines, and that angle is the same as the opposite interior angle. B is also across there on the top right. So we could pick up 2 different rules from here using cyclic quadrilaterals. And let's go on now. The lengths of 2 tangents, remember, a tangent will be a line that's touching the circle at only one distinct point. So we have 2 tangents here. Let's call the points of where they're touching at A and B. Right? And if we draw a line from that point where it's touching, remember, it gives us a 90 degrees. So the 2 points of contact from A and B, what do we recognize? That they are equal. TA and TB are equal. And if we remember from our last video where we gave notes on geometric construction, if we rest our compass at T and open it to the length of A and we swing an arc, by scribing an arc in blue, we will see that it passes through B as well, telling us that TA and TB are the same lengths. So let's reread the theorem. The lengths of 2 tangents TA and TB from an external point T to the point of contact at A and B on the circle are equal. And now we have completed all of the theorems. So we have done past paper questions, which appear in paper 2, section 2, which will be the last 3 questions there. You will find that when they're testing circle theorems, that's normally where it's placed in the paper, in the last 3 questions, one of those. And we did solutions for May 2009, number 10, 2010, 2011, right? So these 5 papers, we already have a video up showing you how to solve those circle theorem questions. And there's another video for showing solutions from 2014. There was none in 2015, 16, 17, and 18. So we have 2 videos on those, and we have a more recent one from 2019 for 3 years until 2022 with a 3rd video. Anything newer than that, we'll have a video with the entire paper's solutions. So here you can study particularly the idea of circle geometry and looking at the theorems there, and look at videos that pinpoint how to solve them. Okay, goodbye.